Okay, let's talk a little bit more about material selection. I put up the ratio analysis diagram yesterday, but before I go to that, I'm still kind of hammering away on cost of different materials, because cost is the big driver of why we use a given material. There are material properties like strength and toughness, but cost is the big driver.
Can you take that out of his sleeve?
This is very simple. Okay. Over the life of a vehicle, the value of a pound of weight saved in an automobile is $2. You can figure that out with the price of gas and what the improved mileage is with lighter weight vehicles. Over the life of an aircraft, it's $200 a pound, and over the life of a spacecraft, it's about $20,000 a pound. So how do we get these numbers? Well, for automobiles, you just kind of say, well, if I drive an automobile for 100,000 miles, and if I were to take 100 pounds off, then I know I can plot the curve and get the slope of mileage versus weight on an automobile, and I know the price of gas, and I can calculate it. And it works out at about $2 a pound. If for an aircraft, you do the exact same thing. It costs $200 a pound over the roughly, well, a 747 goes for about 100,000 flight hours. We don't usually do it on a mileage basis, we do it on flight hours. But TWA 800 had about 102,000 miles on it when it crashed. And some of the 747s in the boneyard out in Arizona, there's this big desert in Arizona where they fly the B-52s and stuff. You've ever seen the pictures where the satellites take pictures and show that they've taken the wings off these things for the salt treating, and stuff. So the Russians can see that we actually are living up to dismantling these aircraft. Anyway, but Arizona doesn't have a lot of humidity, and so old aircraft go out and get parked in the desert there, whether it's B-52s or whether it's commercial aircraft. And typical life of a 747 before you retire is about 100,000 hours of flight time. And you can go through and you can figure all this out. It turns out vice presidents at commercial airlines have to sign off on anything that's added to the cabin. You know, if you're going to have, why do you have stainless steel coffee pots on an aircraft? Well, you don't have glass because things can rattle around, you don't want them to get broken, right? But stainless steel is lighter weight. And at $200 a pound, you can afford the stainless steel coffee pot on an airplane. You know, start thinking about it. When they put the magazines on for people to read, it's $200 a pound. Now, they may change the magazines, but that extra weight is costing the airline, over the life of that aircraft, $200 a pound. I mentioned the other day about this technology, Bliss technology, which we'll get to maybe tomorrow on friction welding, where they could take 20 pounds out of a turbine wheel by welding the turbine, the blades to the disc, and that means 200 pounds out of an engine, and that's 2,000 pounds off an aircraft, a fighter aircraft. Well, 2,000 pounds off a fighter aircraft is a tremendous increase in payload or distance. I mean, you can trade it off. You either put more fuel on or you put more weaponry on. Okay, but it turns out that $200. I mean, obviously these are round numbers. I actually, Boeing says it's classified, you know, it's not classified, but it's company secret as to the commercial aircraft, what the value of a pound of weight saved is. However, there's an MIT thesis of a student who did his work at Boeing about 10 years ago, and the number in there is $188. Okay, so Boeing's worked it out to more than one significant figure, but they figure $188. I've seen presentations by people from Wright-Patterson Air Force Base that show that it's anywhere from $150 a pound for a commercial aircraft up to $1,000 a pound for a fighter aircraft. Okay, but it also depends on where you take it out, because the faster something moves, the more valuable the weight savings is. Now, for a spacecraft, it's $20,000 a pound. Now, people will argue with that a little bit. A, they don't like the general public to know that number. Okay. And, you know, people talk about, oh, someone was just telling me last week that the Soviets are going to, not just this one guy who paid $20 million to go up in space, but other people are going to have, sell tickets to go up into space and go to the International Space Station. I said, this is ridiculous. You're never going to get the ticket price down to less than a couple of $1 million. Why? Well, if the person weighs 200 pounds, and it costs $10,000 a pound to put them in space, in a space shuttle. The space shuttle, you can go on a NASA website, and if you look at the X-33 space plane, one of the goals of the new space shuttle, or the replacement of the space shuttle, is to reduce the launch cost from $10,000 a pound on the space shuttle to $1,000 a pound. Now, if you're talking about a non-reusable vehicle, basically a rocket, a Minuteman or something, you're talking $20,000 a pound. The space shuttle was an improvement because it lowered the price by a factor of 2. It's only $10,000 a pound to put something into space. And when I told you about those little, I brought in the thing from the X-33 space plane, and I told you it's $10,000 a pound for that composite, hey, no problem. I can afford it if it's going into space. But the problem that people have is, they forget that there's different industries, and not everyone is as price insensitive as space business. And people talk about colonizing space. Well, that's great, $2 million a pop, a ticket. How much do you think we're going to colonize space? And even if you drop it to $1,000 a pound, you're talking $200,000 a ticket. Now this is going to be kind of a rich person's game, and you better have some big payoff. Another way to look at this is to recognize that what I mentioned the first day, that the material cost is only 10 to 20% of the total cost. So if it's $2 a pound for an automobile, and 20% of that is going to be the material cost, how much can I afford to pay for my steel or my aluminum? This comes out of Ashby's book. This is 1980, but it turns out it's not so bad. Material costs have not gone up. In fact, the price of steel has gone down in constant dollars, actually even in real dollars, not even constant dollars. Back in 1980, you might be paying $400 a ton for steel. Today, you'll pay $300 a ton, and that's not constant dollars. That's inflated dollars. I mean, the price of steel has gone down by a factor of 2 because of the overcapacity. But back here, he said mild steel was $450 a ton back in 1980. It's $300 a ton today in the same inflated dollars. But if it's $2 a pound and 20% of that cost, that's 40 cents a pound. That means I can afford to pay up to $800 a ton for that steel to put it in an automobile. If I want to just think of an automobile in general at $2 a pound, let's say somewhere, I think I used the number of 30% as the material cost when I drew these lines. The only things you can build an automobile out of for the main structure. Now obviously I can have a piece of platinum in the catalyst, right? But that's micrograms of platinum. But if I'm talking about the structure, and the structure is going to be the heaviest part of the thing, by and large. I mean, that's just the way it is. I can't use anything other than, I can make a car out of cement, or I can make it out of coal. I can start to use plastics as the structural material. Why don't I use aluminum except in very expensive vehicles? Because I can't afford it except in very expensive vehicles. There's lots of ways to do this, but this really works out. The line up here is, this is for aircraft, and up above here, yeah, I can use diamonds or boron epoxy composites and stuff for spacecraft, because I look at the price. And the problem here is, there's a bunch of dilettantes out there. There's a moron called Amory Lovins, okay, out in the World Watch Institute in Colorado, and he gets the ear of congressmen. He says there's a conspiracy going on. The automotive companies could build 100-mile-per-gallon vehicles today. We have the materials to do it. And he's absolutely right. He says the reason we're not doing it is because there's a conspiracy by the automotive manufacturers. The CEOs want to keep the price of, I don't know what it's, he's stupid, he's a moron. I'm just saying this for public, it'll go on the web. Okay? This is for public consumption. The reason he's a moron is, yes, you can do it, But you know, we're building those vehicles right now. If you go to Indianapolis for the 500, for $2 million, they will have some of the best aerospace composites in that vehicle. I can build that vehicle today, 100 miles per gallon. It'll cost you $500,000. Okay? He just forgot the cost. He's basically, I can't remember the word for it. He's a demagogue. He goes around preaching things to people and basically telling them a half-truth. The problem is, people, some of the congressmen love him. Okay? You know, we got to do something about communicating to the rest of the world about these stupid things. Now, another thing. Bob Sprague was this guy from General Electric I mentioned. He used to be head of General Electric Aircraft Engines Materials Group. He's one level below the vice president. He's retired now. Sprague's first law: whenever you hear something about a new material, write it down because it may be the best thing you'll ever hear about this material. Okay? And this one, Williams, Jim Williams, now dean at Ohio State, was Sprague's replacement, who had this job for about 10 years. And his corollary is whenever you hear the price of new material, write it down because it may be the lowest price you'll ever hear. Okay? Advanced materials are wonderful, and it's great to put them in space. It's great to put them on some aircraft, but it doesn't work in high volume manufacturing. And because of the cost and the strength and toughness, and I've already given you the strength and toughness numbers on steel compared to other things, it turns out 95 pounds out of every 100 pounds of materials made in the world is steel. There's a reason for that. Okay? The worldwide steel industry is a $600 billion a year business. The worldwide aluminum business is $40 billion. It's, you know, different order of magnitude. And if you ever go through a steel mill or a aluminum mill, in general, there's a difference, a whole difference in scale. Okay, just the whole manufacturing. We go back to this guy, which I think I threw up before. This is the ratio analysis diagram that plots fracture toughness versus yield strength. So we're not talking about cost now. But I mentioned the little materials are down here where we get something that snaps and defects control the strength. You'd like to have everything pure plastic, high toughness, and plastic general yielding, but that really, to get that, you're really paying quite a bit of money for some of these things. In general, we have something that deforms, and it's not too brittle. It's what we call elastic plastic mixed mode. And steel can do it at very high strength and very high toughness. Titanium can do it, it's in this region. Aluminum, composites, and even polymers can do it. However, they don't do it at very high strength levels. So on the bang for buck, steel is going to win. And if I were to take the strength, the maximum strength of the material, steel wins on maximum strength, and then I divide by cost, then steel has a wonderful figure of merit. Okay? Turns out iron, element 56, is the most stable nucleus. So this guy in Britain who just passed away a couple of weeks ago didn't win the Nobel Prize, but his co-worker did win the Nobel Prize for proving that the reason we have so much iron in the world and in the universe is because it is the most stable nucleus, and in stars, basically, you get fusion. Okay, you got hydrogen going to helium, and hydrogen going to lithium, and you go all the way up, and you only get to iron because it's the most stable nucleus. You can't get the heavier elements by anything except a supernova explosion. So they won the Nobel Prize for explaining that to the world. All the heavier elements above iron come from supernova explosions. Okay, which don't happen all that often, and that's why those things are more rarefied in the world. In any case, so aside from all that trivia, if you then put density in there, steel loses on density. Okay, aluminum is lightweight. However, aluminum's got 5 times higher cost, but it's got 40% of the density. That means it's on a strength to density to cost, it's about a factor of 2 worse than steel. It's not so bad, but it's not great on a strength density cost basis. you can put whatever combinations of these you want together to get some figure of merit. And I mentioned before that the lightweight is an advantage if it moves, and therefore you put aluminum on you make the wheels. People wanted to make the brakes on automobiles because that's on the axle. That's part of what they call the sprung weight. The axle and the wheels and everything is the sprung weight. You'd love to make that stuff lighter weight. The drive shaft of an automobile, they've made aluminum drive shafts. They've made carbon or fiber composite drive shafts on vehicles. Why? Because that drive shaft's going pretty fast, and you get an advantage when things are moving. They wanted to make aluminum silicon carbide brake pads. One of the problems with aluminum is that it doesn't melt at a very high temperature. Steel melts at 1600 degrees centigrade, aluminum melts at 660 centigrade. Typically, you get much above half the melting temperature in absolute Kelvin, and you run into some problems. Well, at 660, you only have to be at about C. That means it's about 900 Kelvin. That means 450 Kelvin is half of the absolute melting point for aluminum. Well, 450 Kelvin is about 175 C. It turns out these aluminum silicon carbide, not brake pads, but basically the disc or the things that hold the calipers for a disc brake, didn't work because when the brakes got really hot and really hard braking, they tended to distort. That's not good. You tend not to have the same force for the braking. Your brakes stay. You die. People don't like that. Now, it turns out the Concorde, when it used to fly, and it will soon fly again, they say, but the Concorde is not flown on speed. It's flown on skin temperature. It turns out the life of the Concorde aircraft is controlled by the heat-treated aluminum alloy, and they actually have sensors, and on a good cold day up there, you'll make it across the Atlantic faster. Because they can go faster. But the problem is they're going to wear out their aircraft if they go too fast because of this frictional heating on the skin. So aluminum has that kind of problem. It also has, as we showed, a lower toughness inherently than steel. Aluminum also, in some ways, it's better corrosion resistance than steel. In other ways, it's not. These are some washers that come off a Black Hawk helicopter. And it turns out these particular washers had a heat treatment. They're 7075 alloy. That was called a T6 heat treatment to give it the maximum strength. The problem is these particular washers had some residual stresses in them from the manufacturer. They weren't supposed to, but they did. And they found them on the shelf, cracked. Now these have cuts in them because I was measuring the residual stresses in them at one point in time. But they have residual stresses of 8 or 10 KSI, okay, 8 to 10,000 pounds per square inch. Turns out that in this particular case, with the T6 heat treatment, you get something called stress corrosion cracking at 3,000 pounds per square inch. So these things could crack sitting on the shelf in the air. And people found them, never used, as spare parts in the military supply, cracked on the shelf. It turns out that if you do the T73 heat treatment, which is an overage, the stress corrosion cracking resistance goes up to about 20 or 30,000 pounds per square inch. No problems, okay? Now the interesting thing about this is the presidential helicopter is a Black Hawk, basically, okay? The problem is, turns out, Sikorsky knew about this because the Navy had problems. They were the first ones. It was some other helicopter. It wasn't the Black Hawk, the Seahawk. But the Navy had a problem because Sikorsky had the same type of design in the tail rotor of their other aircraft, and they switched that entire fleet out and they replaced all the washers and replaced them with T73 because the Navy had some problems and found some cracking. Why is the Navy going to find it before the Army? Because they're out in the ocean, right? Things crack in the ocean more often than in the on the land because of the chloride environment. Well, it turns out there wasn't communication between the Black Hawk program and this other program, and so it turns out it wasn't until later the Navy rediscovered the problem in Seahawks that Sikorsky says, "Oh, we should change these out. So they had 1,500 of these washers on order when an Army helicopter went down in Arkansas and killed 6 soldiers and put one of them in a coma. Actually, I guess the coma person died there. Anyway, so it turns out that they had them on order. It took them 1.5 years to get them, and unfortunately these other 7 people died during that 1.5 years. But they have changed them out. But I've always thought, gee, that's what a presidential helicopter do, you know? So could have taken the president for a real spin when the tail rotor goes out. So aluminum has the same type of problem. Magnesium is even worse. Magnesium, as a structural metal, has about half the density of aluminum. That's wonderful. People have been saying for years that we should put magnesium in cars to lighten the weight. About all they can do is, the biggest piece of magnesium is a beam underneath your dashboard. Because the problem with magnesium is it corrodes too easily. In fact, it corrodes wonderfully. The Navy and Port Hueneme actually developed a graphite magnesium composite that they called a super corroding alloy. The graphite was the cathode and the magnesium was the anode, and they could do several things with this. One is a diver could take it down and he could just, in a plastic little pouch, and he could break the plastic pouch underwater, and it would corrode so fast it would generate heat to keep them warm if it was cold water. Okay. The other thing is it would generate hydrogen so quick they used it for salvage operations. Okay, you take this down, put it in plastic, you go down and put some sort of canopy over what you want to salvage, and you break this open, and you get a big hydrogen bubble that rises the thing to the surface. Right? It corrodes so great. I mean, Professor Latanson in corrosion tells a story about you can't even do metallographic polishing of these things in a water solution because it corrodes faster than you're polishing it. Okay, magnesium wants to go back to its oxidized state, but it's very light. It's very reactive. It's tremendous problems with stress corrosion cracking. I have a student just graduated, went to work for one of the automotive companies. Just sent me an email. His job is to figure out how to join magnesium because they're trying to save weight. I said, well, don't fusion weld it because you'll always end up with residual stresses. And just like these little washers, magnesium's got stress corrosion cracking problems big time and residual stress problems big time. Don't even bother to try to fusion weld magnesium. You can adhesively bond it, and that's about it. You can fusion weld it, but then you have to stress relieve it afterwards. It's not worth the cost. Titanium, it's 100 to 200 times the cost of a lot of other things, like steel. Has excellent corrosion resistance. It's one of the best things in the world. That's why they use it as implants in the body. Has significantly less toughness than steel, better than aluminum. We have class in here until 9 o'clock. It has another problem in engine components. It gets above 900 degrees centigrade and its protective aluminum oxide skin goes away and it burns. And so you start a metal fire in the engine, and you can consume an engine in less than 10 seconds. Okay, with a titanium fire. Nickel and cobalt have 50 to 200 times the cost of steel, but they have excellent high temperature properties. But basically, you get down to it, in terms of structural metals, steel is clearly the one of choice. These others, you don't have to go through too hard to figure out some of these things. One of the reasons for going through this is because people will go out there just like Amory Lovins, and they'll tell you this wonderful material. And unless you're in the Air Force working on space-based programs, most of the time your question ought to be, what does it cost? What does it cost to be fabricated? And the rules of thumbs I've given you are, they keep coming back. I mean, I've been talking about this for 20 years, and so I've had plenty of opportunities to check it. Another way to check it, these things, the HSLA 65 program for the Navy. They want to go from a 51 KSI steel for the hulls of carriers to 65 KSI. Newport News did a big study, and they came up with the cost savings are $10,000 a ton of weight saved. That works out to $5 a pound. Okay. So it's not in that vehicle, it's not a car, but it's actually going to go farther and longer than the average car. And so yeah, you can actually take the kind of car type of cost and extrapolate it out and say, well, it's got 2.5 times the useful life of the car, and therefore it's $5 a pound. You can take this rule of thumb that it's the fabricated cost is 10 to 20% of the material cost, and that type of rule of thumb works there too. I mean, I don't know how much Newport News charged the Navy to come up with that number. I could have done it on the back of an envelope. Okay, they said $10,000. I'm sure they had some engineer, some young engineer, go out and probably spend a week trying to figure out what all the savings were, and they came up with some ballpark number. But you can do it back of the envelope. Okay, you say, okay, what's the cost of the material? It's going to be $1 a pound. Okay, 20% of the cost is the material cost. 20% into $1 is $5. $5 times 2,000 pounds is $10,000 a ton. Okay? I wish I could have gotten a week's pay for that. Anyway, okay, we'll see you tomorrow. Last time we were talking about properties of metals and how you select structural materials. We could talk briefly about ceramics, which I'll hand out some ceramic scissors here. Before I do it, let me put up this, and just plug it in. The fracture toughness diagram that I put up a couple times already.
Can you take that out of its sleeve?
For what I need, I'm not sure. Let's see. I basically put this up before and said ceramics are way down here. You want to work up here in this central region of fracture toughness. You don't want to work down here in the fracture toughness of ceramics. Typical fracture toughness of a steel might have units of 100 KSI per square root of inch. A ceramic might be, a good ceramic is 1. That's 2 orders of magnitude lower fracture toughness. We're going to talk in a little bit about why ceramics are not necessarily structural materials. Although, there's an exception to every rule. In this case, the largest volume use of any structural material, or second largest volume use of any structural material, is a ceramic. I mean, the first largest volume is gravel. It's a structural material. And the second largest volume is concrete. And that's a ceramic. And it's very brittle. And it has a load. But what do we do with the concrete? We reinforce it with steel for whenever it's in tension. It's great in compression, lousy in tension, so you reinforce it with steel. A number of years ago, the Japanese were very interested in ceramics. I remember when I lived in Tokyo in 1985, they had a ceramic fair at Shinjuku, and 2 million people came to this show on ceramics. I mean, the Japanese are very interested in technology. You couldn't imagine 2 million people coming to a material show on ceramics in the United States unless they thought they were looking at pots, or something, different type of ceramics. So anyway, here's some Japanese scissors made out of ceramics, out of basically aluminum oxide. That's why it's a white ceramic. This one I haven't played around with much, and so it had the wonderful thing about ceramics is they're so hard that they'll stay sharp for a long period of time. That is, unless they chip, which if you look at this, you'll see on both of these, if you look carefully, you'll see chips. And so at that point, they're very difficult to sharpen. This one, you can actually kind of feel some chips. If you close it carefully, you can feel some rough spots. Turns out I just bought some, I like to cook, I just bought some silicon carbide aluminum oxide, or zirconium oxide knives, which are really sharp. Okay, these are the types of things, you hold up a piece of paper, you just go like this. They're as sharp or sharper than a razor blade. They cost a couple $100 a piece for a little knife like this. But if you're cutting onions, anybody would know why you need to cut an onion with a sharp knife? You won't cry if you cut an onion with a sharp knife, because you're not crushing the cells and letting all the juice out of the cells. You're slicing through. If you actually slice through the cell walls, then you don't squeeze. You're not just mushing the surface. So if you don't want to cry, if you don't like crying when you cut onions, make sure you get a sharp knife. Another cooking tip from yours truly. Anyway, no one else in my family likes to use these, which is just fine. But they're better than these, and they hopefully won't chip. If they ever do get dull, they basically say ship them back, and they have a lifetime warranty. They'll resharpen them for you. However, I know I went out and got some diamond hones, so I can actually, with diamond tools, you can hone them yourself. But nonetheless, so ceramics have very, very low fracture toughness, and people were talking about the high temperature capability of ceramics, which is well beyond metals. And that's why we coat turbine blades with ceramics, because of the high temperature capability. However, they tried to build monolithic turbine engines out of ceramics. The problem is the critical flaw sizes for fracture tend to be on the order of the size of the diameter of a human hair. And that gets to be something you can't measure. And how do you know that's true? Well, you go back to basically the fundamental equation of fracture mechanics. Griffith came up with this in 1925. He was a scientist in Britain, and he went on, after he came up with this fundamental equation of fracture mechanics, he went off and did something else that was totally outside the field of science for the rest of his career. But nonetheless, there's this factor K, and I'm going to talk about what that is equal to the stress times the square root of pi times the crack length. And the crack length we're talking about here, if I'm talking about an edge crack in a material, we're talking about a crack length A. If I'm talking about a center crack in a material, I'm talking about a length 2A. So basically, you just mathematically make this symmetric, and it becomes an edge crack in terms of what you're interested in. Now, K has units. If this is stress, which has units of thousands of pounds per square inch, and this is pi is just 3.14, has no units. A has units of inches, so the units are KSI square root of inch. Or if you're in a metric system, megapascals, meters to 1/2, or newtons per, they usually do millimeters to the 3/2 power. Right? Okay? It's not exactly something that just kind of intuitively pops out to you what the meaning of this unit is. Okay? However, we can go back to that simple little edge crack, and we know that by putting a defect in the surface of something, I can weaken it substantially. But what am I doing? You see the bending moment I'm putting on this? I mean, I'm pulling in tension, but I'm putting a bending moment on it. And in fact, the bending moment increases with the length of the crack, right? It's just the crack length is essentially, it's just a stress in tension times a lever arm. Only it turns out, the mathematics works out, that it's the square root of the lever arm. Okay? Now, there are whole books that solve what this stress intensity should be at the tip of the crack. What Griffith did, so he said, well, the stress, the nominal stress on the whole thing is a certain amount, but the stress right there at the tip is concentrated, right? And that he calculated what the intensification of the stress is because I've got this lever arm pulling on it. Okay? So basically, K is a stress intensity. That's what Griffith calculated. And there are whole textbooks that do nothing more than calculate the stress intensity for different geometries. And I always put K is equal to, or almost always, sigma. If you're talking about a pure edge crack in plane strain, there's actually a factor of 1.12 in front. And then other people divide the whole equation by Q to allow for other variations and all kinds of things. Make a whole course complicate a simple problem or a simple concept, make it unintelligible. That's what academics do. Okay? Take something simple and make it so complex you don't understand it. Okay? And in fact, many academics tend to think that the more complex they can make something, it shows how intelligent they are as a teacher, which is sort of foolish, because if you're really a good teacher, you're going to make it simple, right? That's teaching. Making things anybody can make something complex so no one can understand it. Trying to make it simple. As Einstein said, as simple as possible, but no simpler. In fact, Einstein didn't say that originally. It turns out Occam's razor, there was this philosopher in the 1400s, said keep it simple. Nowadays we call it the KISS principle. Whatever you want to call it. 99.5% of the time, you don't need the 1.12, you don't need the Q, you want to know what ballpark you're in. I want to know, is my critical flaw size 3/1000 of an inch, or is it 3 inches? It makes a difference, okay, in terms of what I have to inspect for in the structure that I'm going to fabricate. It turns out that for typical fracture toughnesses of ceramics, you can put in anything you want, but if K is on the order of 1 KSI per square root of inch, and so if this is 1 in KSI, and I'm going to put 10 on here, right? And 10 KSI is not a very high stress. You can put 20 or 30 on, but I prefer 1 and 10 because I can divide that without any difficulty. So that's a 10, and so K over sigma is a 10th. I square that, that's 100th, I divide by 3, that's 1/300th, that's 3 mils. There's your 3/1000 of an inch critical flaw size for a ceramic. Did that without even pulling out a calculator. I didn't even have to go to a gigahertz computer to do that. If, on the other hand, this is 100, and I apply a stress of 50 KSI, that's 2. If I square, and K over sigma is 2, right? I square 2, I get 4, I divide by 3, the critical flaw size is 1 1/4 inches. That's a metal. Critical flaw sizes are on the order of inches, unless I'm talking about really, really high strength metals, like aircraft landing gear, where the fracture toughness is like 300 KSI or something. If I go back to these ratio analysis diagrams, you'll see as the yield strength goes up higher and higher, the fracture toughness in KSI square root of inch goes down, and I start running into problems. In fact, I get below 100 at 300. Let's take an aircraft landing gear that I make out of a super duper steel, and it's got a fracture toughness of 70, let's say 75, and sigma has a yield strength of, let's say, 100, has 300, but I'm not going to operate more than about half of that because I don't want to get any high cycle fatigue or low cycle fatigue going on. So this is 150, this is 75. I divide K over sigma as 1/2. I square 1/2, it's 4. I divide by 3, or 3.14, that's 1/12. My critical flaw size is 2 millimeters, okay, on aircraft landing gear. Now I can find 2 millimeter flaws, but I got to be careful because I could miss them, right? Yeah.
So when you get a flaw at that size, that's the size at which it'll propagate through the rest of the material?
As a little fracture, catastrophic, okay?
Does that have anything to do with the geometry?
Yes, it does have. That's where there's a whole book. And instead of one, which is what I use, the number may be 1.12, it could be 0.98, it could be 1.2, it could be all kinds of different things, but if you want to be accurate within 20%, you ignore the book.
You ignore the geometry.
You ignore the geometry. When I say accurate within 20%. This is all for simple tension. If I have shear, okay, if instead of pulling on my paper this way, I'm shearing the thing, I'm ripping it this way, then you have a different fracture mode. And so now you have to, I would actually have to go to that textbook and look. Okay? And maybe there's a factor of 2 difference. But in general, if I want to be accurate within a factor of 2, which in terms of estimated critical flaw size, which is in the square root, remember? So if I want to be accurate within a factor of 2, I only have to be accurate in my stresses or my geometric effects within a factor of 4. Okay? What do I care whether it's 2 millimeters or 4 millimeters? You know, that's flaw size. I do care whether it's 4 millimeters or 30 millimeters. That's a difference that I care about. But if I just want to get the ballpark, then it's easy to do it from this. Other questions?
In this case, are you looking for a single flaw that's that size, or I mean, normally, don't you take like an area and you count the number of defects? I know in a lot of welding processes you do that, and it's
Right.
So like a percentage or something to that effect.
Well, surface flaws, first of all, not that I'm going to answer something else before you question. Surface flaws are more harmful in general than internal flaws. Why? Because often the thing is loaded in bending, and the bending, the surface stresses are higher than the internal stresses, which are closer to the neutral axis, right? So internal flaws are harder to detect, but they're not quite as bad. What your question is asking is, what if I have a cluster of defects, right? Turns out the mathematicians can't handle that. And basically they say, in the worst case, you say, okay, well, let's treat it as if the whole thing is one big flaw, right? The limiting case is, well, you treat each one as the smallest flaw and calculate that and assume that there's only one flaw. In the worst case, you take all of them and link them together as if they're one flaw. The real answer is somewhere in between. The answer in between, if you've got lots of porosity in something, is, you know, such a wide variation that it's very, very difficult for someone to calculate it in those cases. Typically, in a welding spec, it'll say something like no more than 6 pores per 12 inches of weld. Well, you're talking pores that are less than 1/8 of an inch in diameter, because if it's greater than 1/8 of an inch, it's rejectable, usually. So 6 and 12 inches, you know, well, that means they're on average they're every 2 inches apart, so they actually are individual. Now, if they're clustered, and sometimes the spec will say, if they're clustered, it'll have some other rejection criteria. Okay. When I went to work at Bethlehem Steel, the guy in the office next to me was working on the cluster problem, trying to understand it, because the fracture mechanicians, the people who do the calculations, can't handle multiple defects. Mathematically, it's intractable. Okay. Because you have to assume what's the relative strength of the material, the ligaments in between these flaws. And that is a function of how brittle the material is. Well, the brittleness of the material, K is actually not just a stress intensity, that's the other meaning. K can also be a material property. So this equation is used in two completely, in a sense, completely different forms. If I want to know whether a structure will fail, I need to know 2 of these 3 parameters: the stress, the flaw size, and the fracture toughness. And the question is, if the fracture toughness of the material is less than the stress intensity, then I get a catastrophic failure, which is answering Chris's question. Okay? If I got a rubber band, which has a very high, relatively high fracture toughness, I can stretch on that thing and the rubber band doesn't snap. If it's a piece of paper, I can put that same flaw in there and it doesn't take much force before I exceed the fracture toughness of the paper. Okay? So we use the same letter, K, to talk about fracture toughness. We also use it to talk about a stress intensity. So you have to be careful, because in the same conversation, people can switch the meaning of what K they're talking about. It has the same units. And what you're really doing is, you're saying, if I want to use K as stress intensity, this is the measure of the stress intensity, but whether something will fail is K stress intensity greater than or less than K of the material. Catastrophic failure occurs when this is lower than that, when the stress intensity gets greater than the material can support, you have a catastrophic failure. Does that answer your question?
That's KIC, right?
That's what the material property is usually K1C, C for critical. Also, sometimes instead of A up there, they use C for the crack length. So some people may say K1C as the critical crack size, but basically it's critical. K1 is mode 1, which is pure tension. K2 is shear. And K3, let's see, I may get 2 and 3 backwards. If I remember, K2 is this way, well, K1 is this way. K2, I think, is this way. And K3 is shearing, pushing one down and pulling one up. Okay? So there is a K2C and a KC3, but we hardly ever see those anywhere because people don't usually measure them. Cracks do fail that way, but most cracks are simple bending, and simple bending is K1C. K1C is a material property. I can go look it up. When I gave you numbers for fracture toughness for materials, I was giving you typical values of K1C for those materials. And now the question is, does that exceed the stress capability or the stress intensity of the material? Okay. Other questions? Yep.
We have a rod, and it's a circumferential score.
Yep.
How do you measure A? Is it the length of the score around it or the depth of the score into the rod?
Oh, I'm talking about circular rods.
Yeah.
So I got a notch like that. So what you're saying?
But it goes all the way around.
Well, it's the depth in. You basically take a plane out of this, a radial plane, an RZ plane,
Right.
and you just look at it as if it looks like this.
Okay.
So A is that. It's not going all the way around.
That's what I thought.
Okay. Well, I take it back. That's true for a tension, where I'm pulling. If I'm actually twisting, if it's in torsion,
Yeah.
I think if it's in torsion, I may have to go back to my fracture mechanics book and look and see what the value is. Because in that case, I got to stop to think about what it is. It's probably still that value, but the pre-exponent or the geometric factors might be 2 or 3 in that case. I have to look at it. Okay. Other questions?
When you do an impact test, if it's a Sharpie specimen,
Yep.
that's basically just like a mode 1 tension test because you're pulling that egg
It's
across.
similar to mode 1 tension test, but there are debates, there have been debates for 40 years. Can you correlate a Sharpie impact specimen? A Sharpie impact specimen is just a 1 square centimeter, it's a 1 centimeter on the side by 10 centimeter long rod with a 2 millimeter notch in it. So it looks just like that edge crack specimen, and you hit it with a big hammer, and you get an energy in foot-pounds. Well, foot-pounds is not the same as stress times the square root of inch. Okay, one's an energy, one's a stress intensity, and the two of them don't have same units. There are correlations between Sharpie values and fracture toughness values, K1C values. The problem with Sharpie values is the Sharpie was invented about 100 years ago. It's a very inexpensive test. You can get them tested for 70 bucks a pop or so. And it's a good quality control, go, no go. You know whether the steel's brittle or whether it's not brittle. You cannot use directly the Sharpie fracture energy in a fracture mechanics calculation. What you need is the KSI square root of inch number. There are correlations, they're not perfect, and people still argue. I mean, academics argue until they're blue in the face about are the correlations any good? Well, they're better than nothing if all you got is a Sharpie value, okay? And usually all you have is a Sharpie value if you're talking industrially, because a K1C test is not $70, it's a couple $1,000.
I thought you were using the Sharpie value to get a fracture stress and then relate that fracture stress to the geometry and the flaw size, and then you develop KIC from that.
Well, there's something called an instrumented Sharpie where we put it on an oscilloscope, and the Sharpie fracture occurs in a fraction of a second, a few milliseconds. But now we can put sensors on there, and for $500 a test, you can do an instrumented Sharpie, and you can get a fracture load. And from that, you can get what's called a J integral, which is sort of an equivalent K1C, but for a ductile material. K is really for brittle materials. There's something called the J integral, which Professor Rice up at Harvard for his doctoral thesis, basically invented the J integral. The J integral, we talked about it the other day, and you do a load displacement curve, okay? Load P times displacement. Basically integrate the area under that thing for a ductile material. Brittle material goes like that, okay? And fractures, and the area under that's not very high, and so basically you just measure the kind of the peak stress intensity. But for a ductile material, where the thing stretches into forms, you have to do what they call a J integral, which is a sort of equivalent fracture mechanics number to this. Okay? Now I may have missed your question. Give me your question again. So you're not getting a stress out of a Sharpie. You can get that kind of curve. People are still debating whether the Sharpie test is the appropriate way to do it, because the J integral test should be a slow bend, not a rapid bend. And steels do fracture differently under very high strain rates than they do under low strain rates. So you don't really get a stress out of a Sharpie. You can get a number that some people can argue is equivalent to a stress, but other people argue that it's not correct. Because actually what they also have is K1D, which is the dynamic fracture toughness, which a Sharpie starts to relate to the dynamic fracture toughness. But for example, a steel could be brittle under high strain rate loading at room temperature, but ductile under slow strain rate loading at room temperature. At minus 150, they're both brittle, but at room temperature, one slow loading could be ductile and fast loading could be brittle. I mean, it gets to be pretty complex. And if you go to a fracture mechanics books, there are probably 20 different ways they redefine K. K1C, K1D. There's a K1A that's different than K1C in some books. You know, it's an alphabet soup of mechanicians gone berserk. Okay? Does that answer your question? You're still looking a little quizzical at me.
No, yeah.
You're happy? Okay. Because that's the end of the class for today. Okay.